with the I can statements a little bit. So, Michael, can you read me the first I can statement there? Good. Discontinuity. All right, Ashley, can you read me the second one?
I can demonstrate the continuity of the
Perfect. Okay. Kobe, can you read me the third one, please? Perfect. All right, and then Henry, can you read me the last one, please?
I can find the missing value to make a function continuous.
Perfect. All right. I extended this lesson quite a bit. It's going to review some of the limits that we have done before, okay? But as kind of a little mini reteach within the lesson, but it all still goes with continuity, all right? Continuity is an important concept, so we're going to spend 2 days on this lesson. So we'll spend today and tomorrow. Hopefully we get through the whole thing in those 2 days, okay? So this first thing here, and this is why I really wanted to, I decided to wait and have do the lesson together, was to kind of see these pictures together. So these are things in real life where things have become discontinuous. Okay. In 2019, February 2019, there was we had all those rains and the road in Idlewild washed out. So there was a huge hole. So that's definitely a discontinuous road. This one I borrowed from someone else. So this was the Bay Bridge in Oakland. There was an earthquake, and this was my hometown that happened. Remember the first 7-point earthquake a couple years ago up in Ridgecrest? That's where I grew up. And the road actually became discontinuous because of the earthquake. So it's still interesting to watch. It was interesting to watch the Facebook posts from my old cross country coach. He posted all the stuff that was going on with all the earthquakes and stuff. All right, so we're going to look at first of all 3 aspects of discontinuity, and then we're going to kind of flip back into limits a little bit, and then we'll go back to continuity. Okay, so continuity implies no interruptions in the graph. Up to this point, we've basically said, hey, if I have to pick my pencil up to draw it, it's discontinuous, okay? This is a little bit more of an official definition, okay? But it's still the same basic thing. If I have to pick my pencil up to draw it, it's discontinuous somewhere, okay? All right, so there are 3 criteria. I don't know why the box disappeared for my third spot. Apparently my third spot disappeared. So there should be a third box here. I don't know if it's on your notes or not, but on mine it apparently disappeared. So in order for a function f of x to be continuous at a point, we only talk about continuity at a single point, okay? The following three have to be true. So you have to have f of c is defined. So what that means is it has a y value. There has to be a y value. Okay? Doesn't look very good, does it? Let me write that a little bit bigger and better. Defined. So that means a y value has to exist, basically. All right. And then the limit as x approaches c of f of x must exist. And finally, we have to those 2 things need to be equal. So if the y value has to be equal to the limit. If the y value is not equal to the limit, then it's not continuous, it's discontinuous. So we would say that the limit as x approaches c of the function f of x equals f of c. Again, c is just some x value, some number. Okay, so in 1, 2, and 3, there's kind of a 2a and 2b. We are going to talk about why they're obviously discontinuous, right? We're talking about continuity. They're examples of discontinuities. We're going to say why they're discontinuous. Okay, so that way it's going to kind of relate to the 3 things that are there. So, looking in number 1, the first thing that we have to have at C is an actual y value. So do you see how in this graph here, I don't have a solid dot anywhere on that C? So there's no solid dot, so that's why it is discontinuous. So this is the reason for this one, is because f of C is undefined. There's no y value at C. All right, looking at 2a and 2b there. So what do you notice about the limit here? As we're approaching both sides, ooh, that's not the color I wanted. As we're approaching both sides from C, what do you notice about the limit? It doesn't exist, right? It's approaching from the right and the left, and there's definitely a jump going on. It doesn't exist. So that means it's discontinuous there. What about this one here? Look at the limit there. The right and the left matching there. Yes or no? Are they both going the same direction? No. So it's definitely discontinuous because of the asymptote there, right? So that one, the limit does not exist there on either one of those. So this is an example of the limit as x approaches C of f of x does not exist. Okay, let's look at that last one. So on this last one here, do we have a y value? Yep. Okay, do we have a limit? Yep, those look good. 1 and 2 checked off the list. Are they equal to each other? No. So this is the example of, hey, we've got all those things, but they're not equal to each other. We would have still had to pick up our pencil to draw it. So this would be that the limit as x approaches C of f of x does not equal f of C, meaning it does not equal the y value that we had. Okay, so here is where we're going to insert the new note pages. Okay, hopefully you grabbed them or you downloaded it. If you downloaded the file, it was already inserted into the file. Okay, so this is the new one. It's going in at this, so page 29, page 30. So you're going to put, this is the new page 30. Okay, and I just didn't photo, I figured you could deal with there's going to be 2 page 30s or whatever, right? You could just insert this in there. So these pages will go in, and then we will start the other notes we probably won't see until tomorrow. Okay. All right. So I'm going to bring this example up periodically when we're talking about graphs in whatchamacallit. We're talking about graphs in calculus. Okay. When we're talking about graphs, we usually call them curves. Even if it's a line, I will say the curves sometimes. Okay, so even if it's a line, we call them curves. And you can think of them as roller coaster tracks. And I will periodically use, I don't use it that great, but I will periodically use this analogy of a roller coaster. Okay? So we are on the roller coaster. And basically, we don't want to ride a roller coaster that's discontinuous somewhere, do we? That would not be very exciting. It would be kind of terrifying, wouldn't it? All right. So the x values stand for where your friend is standing on the boardwalk, or where you're standing on the boardwalk. So in the analogy of the roller coaster, x is where your friend, so you're on the roller coaster, your friend is not, is standing on the boardwalk. So roller coasters on the East Coast are typically on like a boardwalk. So you got to think of this as like the walkway underneath the roller coaster. That's what we're calling the boardwalk. Okay, and your friend is standing underneath it. That's what the x values mean. We're standing and we're looking up at the roller coaster, okay, above us. The y values, okay, and remember y values, a fancy name for y values is f of x, okay, and those stand for the height of the roller coaster track. So f of x is the height of the roller coaster track. All right. So continuity is when you can draw your graph or your roller coaster track without lifting your pencil, which that was kind of our unofficial definition up to this point. Pencil, pen, stylus, whatever you're using. Okay, a couple of hints. If you have an open circle, these are just reminders. These are things I know you learned last year, and you should have learned, we should have already talked about a little bit this year. If you have an open circle, that means you're going to use a parentheses or a less than symbol, and it means it does not include that number as part of our interval. And then a closed dot means that you're going to have a bracket or a less than or equal to, and it does include that number in the interval. All right. In the roller coaster analogy, you should think of the limit as the height that the two roller coaster carts are coming from different sides will collide. So if your two roller coasters are coming from different sides, they're going to collide at the limit. Again, not a roller coaster I'd want to ride. I don't want two of them coming together and slamming into each other. Okay. So in this first part of example 1, okay, it says f of 6. That means we are finding the y value. Okay. So I'm going to go to my graph. Okay, I'm going to go find this x value, and I'm going to find the y value that gets spit out. So f of 6, what happened? I don't have f of 6, do I? It probably should be -6. It's a typo. Let's make it a -6. So make it -6. F of -6 equals. Okay. All right, let's look at -6. So when I go to -6, what y value is it spitting out at me? Looks like 1. Perfect. All right. F of -1. So f of -1. Ooh, what y value is it spitting out at me? 3, right? I have to use the solid dot because we're actually looking for the specific y value. I think I can erase. There we go. All right, f of 1 is the next one. F of 1, what y value is it going to spit out? 1, perfect. And then f of -3, what y value is it spitting out? 3. Okay. The next thing it's asking me is the intervals where it is continuous. Okay. So it looks like I've got discontinuity here and here. So I'm going to write the intervals where it's continuous otherwise. Okay. So what's my first interval? What's the very first x value that I'm going to use? Approximately. There we go. I can live with negative 7.5. So negative 7.5, it was something that was closed, right? It was an endpoint, so it was closed. All right, where's that interval going to end? -1, perfect. And that, because it was an open circle, we're going to use an open parentheses. Okay. Did we learn the union symbol last year? Did we learn the U in there? Do you guys remember? I don't remember if we did or not. We're not going to use it, so don't use the union symbol. It's safer to put commas because there's some weird math property where it isn't proper in some cases, so it's easier to just make a list with commas. Okay, I don't want us to use the union symbol on the AP test and lose the point because we've conjoined something incorrectly. Okay. All right. My next interval starts at where? -1 and goes to where? 1, because I still got to get this piece in here. That's still continuous in there. So I'm going to go -1 to 1. And I think it was, let's see, that was still open, right? All right. Then I'm going to go from -1 or 1 to where? 4. Should they be open or closed? Closed again. Good. So from 1 to 4. Oops. Closed. Closed. All right. Okay. The next thing we're going to do is we're going to find the limit. I can't see those that far away, so I'm assuming you can't either. The limit as we're approaching each of these x values, and I believe this is supposed to be a -6 again. That's a typo on my part. So make it a -6. All right, so we got to approach the same x and the same y from both sides here. So I'm going to start with -6. Let me erase my scribbles here so far. All right, so I'm looking at -6. Ooh, -6. So from the left, from the right, what's it approaching? 1. Good. All right, looking at -1 next. So -1 is right here. Okay, from the left, from the right, what are we approaching? 1. Perfect. Okay, looking at 1 next. Here's 1. So from the left, oops, that's not what I wanted to do. From the left, from the right, what's going on? Does not exist, right? Because there's a jump there. Definitely does not approach the same number. So this one would be DNE. We're looking at -3. So -3. Okay. From the left, from the right, what's going on? It's at 3, right? So that one was okay. It approached 3. Okay. That should have, for the most part, other than the continuous intervals, should have been review. Okay. All right. Let's look at the next page here. Okay. All right. So we're going to talk about some different types of discontinuities. Okay. And then we're going to, I can't remember if I put this in there again. I did. Okay. Then I'm going to have you try some on your own. Okay. So let's talk about the different types of discontinuities. So a limit fails only if the 2 roller coaster carts will not collide. So 2 roller coaster carts will not collide. So if they won't collide, it's discontinuous. And I couldn't get this little patch of stuff to fit out in the left-hand column, so I just put it in the right-hand column. All right, so this is kind of it. This is now an illustration of 3 reasons why the 2 carts will not collide. They happen to use K instead of C. Okay, it's not a big deal. Okay, and mathematically, these are called a non-removable discontinuity. So what we're looking at is non-removable. We will look at some removable ones eventually throughout this lesson. Okay, the first one is called a jump discontinuity, which we've said that word jump before. All right, so a jump discontinuity, and I'm just drawing an example of one. This is just an example. It could look like anything. It could be something that looks like this. That's a jump discontinuity. The next one is an infinite discontinuity. So there's 4 different versions of this, okay? We're going to use this kind of line here as kind of our asymptote. Okay, so I'm going to pretend that's my asymptote. So there's 4 different ways that this could look. I could have them both going up towards infinity. They could both be going down towards negative infinity. Or they could be pointing in opposite directions, right? I could go like this way. Or I could go this way. I'm going to do it wrong. Like this and like this. Okay, so those are what infinite discontinuities. There's arrows involved typically. They're pointing possibly in opposite directions, but definitely there's an asymptote. Okay. The last type, I'm going to give you 2 names for it. It's an essential discontinuity. You could also say that it's oscillating. Okay. I probably don't need my K, that dashed line there, but I'll show you what's going on kind of near the K. So this is something where you got maybe some kind of a wave function going on, and then it gets closer and closer and closer, and it kind of goes up and down and up and down, and you cannot tell it's oscillating so much that you cannot tell what the limit is. Okay. So, and it gets really cramped together wherever the limit's supposed to be reaching, and you really cannot tell. Okay, no matter how much you zoom in on it. All right. So that's what an essential or oscillating. On that one, I would only expect you to maybe recognize it in a picture. There's probably not going to be any problems on an essential one. Okay. All right. Let's see if I had anything else out here. I don't think I did. Okay, so there's a second example there. I was really trying to squish it in and not kill too many trees. So the graph is at the bottom of one page, and the problem is at the top of the next page. So I'm going to give you a minute. You already know what the plus and the minus mean on there, okay? I want you to actually take 2 minutes. I want you to try that whole problem, okay? So nothing really new. You're trying all of example 2 in the next 2 minutes, okay? So everybody do that. Okay, here's what I want you to do next. I want you to compare with your table partner. Okay, so compare your answers with your table partner. You guys can work as a table of three. Okay, so right now take about a minute or so and compare your answers for the whole problem. All right, let's check them over. Okay. All right, so we're going to use that graph. So we got f of 1. What did we find for f of 1? Everybody good with 3? Okay. F of 0. What did we get for f of 0? Everybody doing okay so far? 0. Okay. F of negative 2. Is there anywhere where it exists? There's no solid dot, right? So what does that mean I write down? DNE, right? Does not exist. All right, f of negative 4. So looking at this one here, where's the solid dot for the y value? Good. Okay. Everybody okay on the does not exist one? That's the one where it sounded foggy. Okay, we've got to do continuous intervals. All right, Matthew, what was the first continuous interval? What's the first x value? Okay, and where did that one end at? Where did I have to pick up my pencil at? Yep. Okay, so negative 5, which I would write close to negative 4. All right. Coral, where's the next one? Negative 4. Okay, where does it end at? Perfect. Okay, and those would both be open. So negative 4 to negative 2. All right, Henry, where's the next one at? Negative 2 and 0. Perfect. Okay, and both open again. So negative 2 and 0. All right, and then Mariana, where's the last one? 0 to 3. Perfect. And we would assume the way this is drawn that it would end right there, right? Not have an arrow on it. If it had continued through that patch, we would have assumed the arrow. Okay, so 0 to 3, and it looks like they're both closed on that piece. So 0 to 3. Okay, and I really should have put commas in there. All right, let's take a look at the limits really fast. So limit as x is approaching 1 of f of x. So limit as we are approaching a 1. So from the left, from the right, what did you guys get for the limit right there? 3. Perfect. All right, so we know that that one's 3. Okay, limit as f of x approaches 0. Let me do some erasing here. Okay, so as we're going to 0, what's going on? Does not exist, right? They're definitely not approaching the same thing. So this is a DNE. Okay, but now it's asking us specifically from the right and from the left. So that does work, doesn't it? So from the right side, what did it go to? From the left side, what did it go to? So 0 and 3. And notice it was written in backwards order too, wasn't it? Normally we do the left first and then the right. So be careful. Watch your notation. That's like a purposeful thing to make sure you're actually paying attention. Like on a test, if I would reverse the order the way we normally do it. Okay. All right. It looks like -2 is the next one. So let's see, -2. What's the limit there? Definitely from the left and from the right is the same, and it looks like 1. Okay, and then finally at -4, looks like the left and the right are the same. What are we getting? 3. Everybody okay? So it's like the third or fourth time we've retaught that skill. Hopefully we can do that in our sleep almost. Okay. All right. Let's now take a look at example, or we're going to look at the left-hand column again. Okay. So a function is not continuous or discontinuous. So we've looked at the continuity and in terms of the limits with a graph. But what happens if we're just given an algebraic function and we just have to look at it and go if it's continuous or not? So we need to have some way to deal with that, just look at it, because we're not going to have a calculator. Okay. We're not going to have the picture of the graph. So either we have to come up with the picture of the graph, or we have to just know by the algebra and the patterns in the algebra what if it's continuous or not. Okay. So some key things to look for discontinuity in algebra. So is if we divide by 0, that's a bad thing, right? Can't divide by 0. So if you're something that when we plug an x value in and we get 0 in the denominator, it's definitely discontinuous somehow. Okay. If we take an even root of a negative number, so we know that we cannot take a square root or a fourth root of an even number, or of a number that whatchamacallit, an even root of a negative. So we can't have a negative under there, but if not, it goes imaginary. And the good news for this year and for next year's class, there's no imaginaries in calculus. Okay. Later on, beyond those 2 years, there can be, but for our purposes, no imaginaries. Okay. We take the natural log of 0 or a negative number. Can't take the natural log of 0, can't take the natural log of a negative. So if we see those things going on, we know it's discontinuous. And then if we have a piecewise function whose heights don't match at the boundary, basically if you plug into the 2 branches and they aren't the same number, then we know that then it's discontinuous. All right. I'm going to not do example 3. I'm going to keep going down the column on the next page because I just couldn't squish it all in. And we're going to talk about these, and then we will go into doing some of the problems. Okay, we'll do as many of them as we can get through. So a removable discontinuity is infinitely small, so the limit will exist. I believe we talked about having holes in graphs. I hope we talked about having holes in graphs. So having a hole in a graph, like, it's infinitely small, and we draw it way bigger than it should be. But having that hole, that is something that what we call removable. Remember, what the hole is going to come from is I factor something out, and I'm going to cancel it. That's where that hole is coming from, and we'll see some examples of that. So I can write another function that is continuous, so that's what makes it removable. A discontinuity is removable if you get 0 divided by 0. So you plug in and you get 0 divided by 0. That's your red flag that was just a removable discontinuity. Okay. A non-removable discontinuity is a large gap, so the limit will not exist. So when you see the jump, when you see the infinite discontinuity going in both directions, okay? So those things are non-removable. There's no way I can write another function that's going to take them away, okay? So there are different categories of non-removable discontinuities. There's a jump discontinuity if you get the absolute value of 0 over 0, or 0 over the absolute value of 0, or piecewise, sorry, I should have told you to write spell, piecewise heights that don't match. Piecewise whose heights don't match. If you need to go into the little example at the bottom of the top of 4, you're probably fine. You probably won't use all that space. Okay. Another type is when we have a number over 0. That's the vertical. You're going to want these 2 pages right here, okay? Okay, so when we have a number over 0, that means number, not hashtag, right? In our world here. So number over 0, or the natural log of 0 only on one side. All right. An essential discontinuity typically comes from a sine or a cosine. So when you see sine and you get a number over 0 when you plug in, or cosine when you get a number over 0 when you plug in, you're going to have an essential. That's the one where it oscillates up and down and up and down and up and down and up and down. We won't see that one very often. Okay. All right. And then there's what we call a complete discontinuity. If we get the natural log of a negative number or the square root of a negative number. All right, we ready? We're going to try some examples. Okay. So, example 3. Are the following functions continuous at the given x value? If not, label what kind of discontinuity it is and if the limit exists there. Okay. So, I am just going to do the plug-in route. Okay, I'm just going to plug in the number and see what happens. Okay. So when I find f of 5, I get 5 minus 5 over, let's see, 5 squared is 25. What's 2 times 5? 10 minus 1. Okay, so let's see, I get, 2 times, yeah, that's right. Something's not going right here. Minus, there's a typo. This is supposed to be a 15, not a 1. Let's switch that to a 15. That'll make a lot more sense now. All right, so I end up with 0 over 0. So, is it continuous? Did I get one of the things on this list over here in the left-hand column? Did I get a 0 over 0 or absolute value 0? Did I get one of these things? Yeah, so is it continuous? No, because these were types of discontinuity, right? So it's not continuous at x equals 5. I'm lazy and I draw the at symbol instead of the word at. Now, I have to classify which type it is. So I'm going to look for that 0 over 0 out in my left-hand column. So I noticed the 0 over 0, and it tells me, hey, that one was removable. Okay, so I'm going to say that that's a removable discontinuity. So it's removable. Oh, no E in it. Removable. All right, let's take a look at B. So again, I'm going to plug in my 2. So f of 2 equals 2 plus 2 over 4 plus 2 minus 6. Okay, what do I get in my numerator? 4. What do I get in my denominator? Oh, so what happened? Is it continuous? Definitely not continuous. So not continuous at x equals 2. That's a 2. All right. Which type is it this time? Look at your left-hand column. Say it louder. Roxana, I think you had it. Is that you? Oh, Nydia, what did you say? It's an infinite. That's correct. It's going to be a vertical asymptote, right? Where was it at? It was this one here, right? So a vertical asymptote or an infinite discontinuity. I would take either one of those, okay? And we will see that more in action in the lesson that's after this one. Not tomorrow probably, but the day after, we'll see the vertical asymptotes come back. So I would say infinite discontinuity. And it's not removable, right? Non-removable, because sometimes the problems will just ask removable or non-removable. It's non-removable. So a non-removable infinite discontinuity. All right, let's look at C. All right, I'm going to plug in my 0. So f of 0 equals natural log of 4 times 0 minus 3. So what do I get inside the natural log? -3. Am I allowed to have that? No. So it's not continuous. Big surprise, right? That would not be continuous at x equals 0. Okay, go look at your names out in the left-hand column. What kind of discontinuity is it? That's a complete discontinuity. Is it removable or non-removable? So look at what the category is right here. So everything underneath there is non-removable. The only one that's removable is the 0 over 0. Does that make sense? Everything else is not removable. So complete and non-removable. Okay. Let's look at this next one. So f of 2 equals the natural log. What's 2 times 2? So 4 minus 4. What's 4 minus 4? Good. So what's wrong with it? Are we allowed to have a 0 in there? No. So is it continuous? Surprise, surprise, it's not continuous, right? So not continuous at x equals 2. Okay, what type of discontinuity? Matthew, what did you say? Infinite, right? Because it was a natural log of 0, so it fell into here. And is it removable or not removable, everybody? Good. So it's infinite and non-removable. Perfect. Okay. Here's what I'm going to do. I'm going to give you, there's like 6 parts to example 4. I'm going to give you about 4 minutes. See how far you can get in 4 minutes. Okay? See if you can figure out if they're removable, what type of discontinuity and removable or non-removable. Okay? And there, I will give you a hint. One of them is continuous. Actually, 2 of them are continuous. 2 of them are continuous. I've got to type, it's the X value, not the exclamation value. I'm going to give you about 20 more seconds, and no matter where you're at, we're going to look at them real fast, okay? See if we can finish up example 4 before the bell. Okay, let's plug in the 0 on A. So e to the 0 minus 0 equals e to the 0, which is, what's anything to the 0 power? It's 1, isn't it? You could make smiley face to the 0 power, it would be 1. All right, continuous, not continuous? That one's continuous. Continuous, because I did not get one of the cases that was in the left-hand column there, right? So continuous at x equals 0. All right, looking at B. F of 2 equals 2 minus 2 over the absolute value of 2 minus 2. I get 0 over the absolute value of 0. Continuous or not continuous? Not continuous. This isn't one we saw in the last example, right? At x equals 2. What kind of discontinuity? Jump discontinuity. Continuity. Okay. I'm going to keep going. Is jump removable or non-removable? Good job. Non-removable. I'm not going to spell it all out. All right. Looking at this one. Oh, I can guess what's coming. F of 0 equals sine of 2 over 0. What type of discontinuity? That's an essential one, right? So not continuous at x equals 0, and it is essential or oscillating. And is it removable or not removable? Non-removable. Okay. This next one, f of 1. So square root of 1 minus 3 is going to be square root of a negative 2. Continuous, not continuous? Not, can't have a square root of a negative, right? So not continuous at x equals 1. What kind of discontinuity? Complete, removable, or non-removable? Complete, non-removable. Okay. All right. For the next two, I don't know if you got that far or not, you have to plug in each branch. Okay, so we have to plug in both branches. I'm going to be probably a little bit sloppy. I'm just going to find f of 1 on both sides here. So 1 squared minus 3 times 1 plus 2. So let's see. That would be 1 minus 3 plus 2. What do we get there? 0. Okay, now I'm going to look at the bottom branch. So f of 1 equals 3 times 1 plus 1. So 3 times 1 is 3. What's 3 plus 1? 4. Did my both the right and the left match? No. So it's not continuous at x equals 1. Okay. What kind of discontinuity? So look for the left hand. Look in the left hand column when I have a piecewise, because that's a piecewise function, right? It's a jump, right? Here it says it right here. Piecewise whose heights don't match. Okay. And I know it's totally counterintuitive to what we just did. Last year I told you on piecewise we don't plug into one of the branches, right? Well, this year we do. Sorry, that's kind of sort of confusing, isn't it? All right. So this is a jump. Jump discontinuity, removable or non-removable? Non-removable. Okay, the last one was continuous. Okay. All right. We will finish it up. Make sure you start taking a look at the assignments. Okay.